Hello everyone, my name is Meena and I'm studying in BTech second year in DSI program at IIT Roorkee. Today I have made a presentation to talk about the topic of spectral decomposition and its application, and also I'll also talk briefly about PC and SVT, which are taught to us in the course DA 201 and applied linear algebra. So, the agenda of this presentation, uh, here in this presentation, I'll talk about what spectral decomposition is, why and how it is useful and how it works, the method, how to apply a spectral decomposition on a given symmetric matrix, its applications, and limitations. And first of all, let's see what spectral decomposition actually is. The spectral decomposition is a method of decomposing a symmetric matrix into its eigenvalues and eigenvectors. It is used to simplify complex problems and reveal the underlying structure and pattern of the data. It is also important because many applications in various fields and problems. It is a special case of spectral theorem, which will come later in the slides, which states that any matrix can be diagonalized by an orthogonal basis of like eigenvectors. Here, the spectral decomposition allows us to write any symmetric matrix as a product of three matrices, let's say U, D, and the transpose of U. Here, the U is an orthogonal matrix whose columns are eigenvectors of the given symmetric matrix, and diagonal matrix whose diagonal entries are the eigenvalues and the transpose of the formed and orthogonal matrix. Here, I'm going to talk about how decomposing a symmetric matrix or any matrix for the fact into its eigenvalues and eigenvectors can help us better understand and interpret the data. Here, we decompose a matrix into its eigenvalues and eigenvectors because they can help us understand the properties and behavior of the matrix and the system it represents. Here, these eigenvalues and eigenvectors tell us about how the matrix scales when a vector is multiplied by it, and also tells us about its direction, which helps us understand the patterns of the data better. Here, eigenvalues and eigenvectors also just to simplify complex problems uh, in in calculation involving matrices such as large powers, inverse determinants, or rank of a matrix. Here, this can help us reduce the computational cost and improve the stability and interpretability of the solutions. And another uses is that it can help us generalize or extend the concept of matrix decomposition to non-square or non-symmetric matrices using methods such as singular value decomposition or spectral theorem. Because here the spectral decomposition is only applied and is only tells us about the decomposition of a symmetric matrix. Symmetric matrix, it does not applicable for the rectangular matrices, but it helps in understanding the methods of decomposition for the rectangular matrices such as SVD or the spectral theorem. This this can help us. This can allow us to apply spectral methods to a wider range of problems and data types. And coming to the spectral theorem. The spectral theorem is a theorem that states that any symmetric matrix can be diagonalized by an orthogonal matrix. That is, it can be written as a product of orthogonal matrix, diagonal matrix, and the transpose of the orthogonal matrix. The diagonal matrix contains the eigenvalues as its diagonal entities, and the orthogonal matrix is formed from the like eigenvectors. This spectral theorem also implies that the eigenvalues of symmetric matrix are real and the and the eigenvectors are orthogonal. The spectral theorem can be generalized to other matrices and operators such as normal, unitary, orthogonal, and Hermitian, as we talked before. Just like I said, A is equal to U lambda U transpose, where lambda is a diagonal matrix, U transpose are orthogonal matrices. And and like how the formula for the diagonalization of a matrix is known to us, like D equal to P transpose AP, where P is an orthogonal matrix. And from this we can compute A in terms of DSP, DP transpose by using the inverses. Here, as we know that the inverse of orthogonal matrix is its own transpose. So by using that rule, we can compute A here. And this equation A equal to P dP transpose is a spectral decomposition of A. And why spectral decomposition is useful, like like I've already said before, the spectral decomposition allows us to simplify complex problems by using eigenvalues and eigenvectors, and helps us better understand the structures and patterns of the data. Here, by spectral decomposition, we are using, there are three processes, like rotation of eigenvectors onto the standard basis, and then by multiplying it with the diagonal matrices, we scale, or I mean stretch or string the matrices, which comes under scaling, and then again multiplying it with the orthogonal matrix gives us the rotation of the eigenvectors which are on the standard basis right now onto its original direction. So like this, it can help us better understand the patterns of data when we are decomposing the matrices into the multiplication of three matrices, and also helps to reduce the computational cost, and helps us better interpret the solutions. It also generalizes the decomposition to other types of matrices. How spectral decomposition works. The basic step uh, for decomposing a matrix is to find its eigenvalues. The general steps for finding the decomposition of some matrix are: find the eigenvalues of the matrix by solving the characteristic equation or using an iterative method. And next, we find the eigenvectors of the matrix by solving the system of linear equation, and then we normalize the found eigenvectors to form the orthogonal basis. And then we form the orthogonal matrix P and diagonal matrix D, and then verify the spectral decomposition of the matrix A. And to see it's working, I have taken a simple 2 cross 2 symmetric matrix A, which is given by 4114. So to perform spectral decomposition of the matrix, we'll first find its eigenvalues and eigenvectors, which is simply by calculating the determinant of A minus lambda I, and using the characteristic equation that of A minus lambda I equal to 0. Which gives the eigenvalues as lambda 1 equal to 5 and lambda 2 equal to 3. Now, after finding the eigenvalues, we find the respective eigenvectors. So finding the respective eigenvectors for lambda equal to 4, we get the eigenvector as v1 as 1, 1. And then for lambda equal to 1, the respective eigenvector is v2 minus 1, 1. After finding the eigenvectors, we normalize them to form an orthogonal basis, which is done by normalizing the eigenvector, and then the process spectral decomposition starts with the constructing of matrix P with the its columns as the normalizing with its normalizing eigenvectors, and then we construct the diagonal matrix lambda with the eigenvalues 5, 3, 8 at its diagonal entities. The spectral decomposition of A is given by this, and here the matrices P and lambda represent the spectral decomposition of matrix A, and the eigenvectors V1 and V2 play a crucial role in understanding how the original matrix A behaves in terms of scaling and rotation, as I've already told before how orthogonal matrix is responsible for rotation. Here, the P transpose rotates the eigenvectors from its original position to the standard axis, and lambda it scales, and the orthogonal matrix again the rotates the eigenvectors which are now on the standard axis to its original direction. And then as you know that the inverse of an orthogonal matrix is just transposed, then we get this P transpose, and then verify the spectral decomposition of the given example of symmetric matrix A, which is 1 by 2 into P into lambda into P transpose. And now let's talk about application, because till now we have seen how spectral decomposition is useful, why it's useful, how it simplifies our complex problems and helps us to understand the data better. And here I'm going to talk about where the spectral decomposition is used in various fields. Like, for example, it is used in PCS, principal component analysis, spectral clustering, signal processing, system identification, linear regression, support vector machines, kernel, SVMs, etc. Here I'm going to briefly talk about how spectral decomposed is used in few of these fields. For example, in principal component analysis (PCA), it's a technique for dimensionality reduction and data analysis that uses spectral decomposition to find the directions of maximum variance in a data set, the maximum variance of the information. Spectral clustering. It's a technique for grouping data points into clusters based on the similarities, which is measured by the eigenvalues and eigenvectors of a matter that represent the pairwise affinities between the data points. It is also used in signal processing, which is used for analyzing and filtering signals such as sound or images. In this method of signal processing uses a spectral decomposition to decompose a signal into its frequency components. And here are the limitations of spectral decomposition. We've already talked a few of the limitations back there, and the main limitation of spectral decomposition is that it's not applicable to all the matrices. It only helps us decompose square symmetric matrices. So it does not tell us about the rectangular matrices. There is a main limitation, and others include computational cost, sensitivity to noise, interpretability. Like it it does reduces the computational cost when it is when a given matrix is decomposed into three matrices. But when a very large matrices, or if the matrix given is sparse or ill conditioned, it can be quite expensive to compute the spectral decomposition for those matrices. It is sensitive to noise. Spectral decomposition can be affected by small perturbation or errors in matrix entities, which can change the eigenvalues and eigenvectors significantly. Interpretability. Spectral decomposition can be difficult to interpret or explain in some contexts, especially if the eigenvalues and eigenvectors do not have a clear physical or intuitive meaning. And here I'm also briefly telling you about PCA and SPD. Here, PCA is a technique, as you've already seen, which is used for dimensional reduction. That is, it projects the data onto a lower dimensional subspace that presents most of the information and variability of the original data. And and also a data analysis that uses spectral decomposition. And here, when coming to SVD, it is a computational method that can perform PCA by finding the eigenvalues and eigenvectors. Here, it also decomposes, SVD also decomposes any matrices into three matrices. Here SVD can be applied to rectangular matrices, not only for square matrices, which limited spectral decomposition. So here the UDV matrices, where D is a diagonal matrix and U and V are orthogonal matrices. Like The columns of U are the left singular vectors, and columns of V are the right singular vectors, and diagonal entities of D are the singular values of the matrices. So that's that, and here, like I said, the SVD is also a method for data reduction. And here, a brief definition of SVD is that a SVD factors as M cross N, which is a rectangular matrix A into a product of three matrices, assuming that all IDs are known. That is A equal to U, D, D transpose, where U is M cross K matrix, E is an N cross K matrix, and D is a K cross K diagonal matrix. K is the rank of the matrix. Okay. Now, application of SVD. Here, SVD is also applied in various fields for collaborative filtering, semantic analysis, semantic indexing, general classification, clustering, and features, etc. Here, the limitation is that it cannot capture polynomial words with multiple meanings. Resulting matrix explanation may be difficult to interpret. Here, as I said, the spectral decomposition is just for symmetric matrices, whereas SVD can handle any matrix, not just symmetric matrix ones. And this means that SVD can perform PCA on no square matrices by using the left or right singular vectors as principal components. SVD is efficient and numerically stable. SVD can find all eigenvalues and eigenvectors of a matrix in one step without having to solve a polynomial equation or iterate over multiple steps, with, which is the case in spectral decomposition. SVD also avoids numerical errors or instability that may arise from rounding or noise, whereas the spectral decomposition is affected by the noise. Here, SVD can provide additional insights into PCA. It can reveal the relation between the original data and principal component by showing how much each component into reconstruction of the data. And as a summary of the give the given presentation, we have learned that spectral decomposition is a method that can simplify and analyze data by using the eigen eigen eigenvalues and eigenvectors of matrices. It also helps us to find the main components and features of the data, help better understand the structures and patterns of the data, and it also helps us to reduce the dimensionality and complexity of the data by decomposing the given symmetric matrix, given symmetric matrix into its respective eigenvalues and eigenvectors. However, we have also seen that spectral decomposition also has some limitations, such as assuming linearity, being computationally costly for matrices which are sparse or ill-conditioned, and by getting affected by the sounds or noises in signal processing, requiring accurate movements, ignoring latent variables, etc. Therefore, spectral decomposition needs to be used with caution and adaptation for different sets and problems. So, thank you for listening to me till now.